My goal in this course is to teach you everything you need to know so that when you set foot into calculus one day, that you'll be prepared and need to know all the things you need to do well in that class. Now, up to this point, the only assumption that I've made is that you know a little bit about algebra. I have a few algebra videos on the market that are excellent primers for everything you're going to need to know with regard to algebra. And what you'll find is typically what happens is you'll go through algebra in school, and then one day you'll take calculus, and there's kind of this gap of knowledge that needs to happen in there. And I'm going to cover that gap here. Usually that class is covered by a course in either pre-calculus or trigonometry. Either course really will get you, I think, pretty much ready for calculus. My goal is to teach you the content of that course so that you're ready to go when you get into class. So let's begin. We're going to start talking about something called complex numbers. So I'm just going to write that on the board. Complex numbers are complex numbers give people a hard time a lot of times. And I think that if I had to pick one name in math that someone made up for some concept and it just totally confused people for centuries afterwards, it'd be this one. Forget about the name. Complex has nothing to do with it, okay? Another word for these things you'll hear, we'll talk about, is imaginary numbers. That's almost even worse. Imaginary makes you think that it doesn't even exist. It's totally useless. I know you may have heard these terms before. My goal is to show you what they are. Okay? Recall for a minute the following. Recall that if we had something like x squared is equal to 5, and when I say recall, I just mean think back to algebra. How would you solve an equation like that? Well, in order to get rid of the square term, what you need to do is take a square root of both sides. So what you would have is square root of x squared equals square root of 5, right? But notice that every time you do something like this, you'll need to put a plus or a minus in front of your square root. And that's just something that you should have just picked up from algebra. So what you will have is x is equal to plus or minus the square root of 5, okay? Or, maybe a different example might be, if you had x squared is equal to 25, okay? X would be plus or minus 5, okay? That means there's two solutions to this equation. One of them is positive 5, one of them is negative 5. The reason is you can take positive 5 and put it in here. Positive 5 times positive 5 will give you 25. You can also take negative 5 and you can put it in there. And negative 5 times negative 5, again, will give you positive 25. All of this has really not much to do with complex numbers, but it's a good intro for what we're going to need, okay? So let's say that we're working with the problem kind of like this. X squared is equal to 25, okay? What if you had, I don't know, just on the test or something, x squared is equal to negative 25, okay? How would you solve a problem like that? Well, you might be tempted to put a square root over this and a square root over this and just kind of leave it like that circled on your paper. Well, that's not going to cut it. Okay, that's not correct. Let's just see what would happen if we just said x is equal to plus or minus 5 here. Let's just pretend that we just assumed this was the answer. We already said that 5 times 5 is positive 25, so positive 5 is not a solution to this at all, because we're looking for x squared is equal to negative 25. Let's say we take negative 5. We put that in here. Negative 5 times negative 5, again, gives us positive 25. So it looks on the surface that there's no number that you can multiply by itself, either positive or negative. It looks like on the surface there's no number that I can multiply by itself to give me negative 25. And that looks like a total showstopper. And in fact, there are a set of numbers that will satisfy this equation. Okay, they're called imaginary numbers. Okay, let me write something down on the board, and then we'll talk about it and we'll understand why it's useful. The answer to this problem, if you take the square root of this side and the square root of this side, we get x squared equals plus or minus, because we always have to have a plus or a minus anytime we put a square root around something. Okay. What you're going to have is you go ahead and you take the square root of whatever it is that's actually under here, neglecting this negative sign altogether. So square root of 25 is 5, okay? But then you put I after it, okay? The answer to this equation, let me get rid of this right here, x is equal to plus or minus 5i, okay? What the heck does that mean? I is not a variable. I is not, not something that you can vary. It's just a constant. It's something that mathematicians made up in order to make this work out. Okay. So what you do is, the short and sweet of it is, anytime you have the square root of a negative number, anytime you take the square root of the number, forgetting the fact that it's negative, you put that down, plus or minus, and then you just stick an I at the end of it because it's negative here. Okay, that's what you do. Now, one more crucial definition in order to make this work out, and I'll show you why. I just told you this was the answer, and I did not tell you why. Mathematicians have defined I to be, by definition, the square root of negative 1. By definition. You can't think of a real number that's going to actually be the square root of negative 1. There is no number you can pick that'll fit that. So they made up a new number, and that number they made up really isn't written as a number, it's written as this letter I. So this, by definition, is equal to this. This is very important. You need to remember this. This definition is very important, okay? So you have to take it on faith for a moment that what I'm telling you is true, and you have to just take it on faith. If this letter I is defined as the square root of negative 1, and if this technique I'm telling you is the solution to this guy right here, then let's figure out if that's true. If this is really a solution, then what we're saying is x squared is equal to negative 25. So let's try it out. Let's try positive 5i. 5i times 5i, what does that equal? And we're going to see it's going to equal negative 25. So we'll put a question mark, equal negative 25. We're going to check it out here. 5 times 5 is 25. That part's obvious. I times I is I squared, just as any old variable that you might choose to think about. And we're asking ourselves, is that equal to negative 25? Well, if I have defined I as the square root of negative 1, if I square I, which is what I've done here, if I square I, then I've squared the right-hand side of the equation like this. Let's just go through in all the detail. And that would be 25 I squared is going to be this quantity that I have just told you is correct, and you're just going to have to believe me. And we're asking ourselves, is that equal to negative 25? Okay. Well, of course, we're going to have the 25 left over here. And you can see that anytime you square the square root of something, all that you're left with is what's on the inside, which is just what I carry around here. And I think by now that you'll be able to see 25 times negative 1 is negative 25, and that is indeed equal to negative 25. Now, that's basically the bottom line. All you need to remember is there's this thing that we call I. It's not really a number, it's sort of something that was made up in order to be able to solve equations like this when you're taking square root of negative numbers. I is defined as the square root of negative 1. And so anytime you're confronted with the square root of a negative number, you just take the square root of the number, neglecting the fact that it's negative. You write that down, you put your plus or minus, and then you write an I at the end of it. Okay? Now notice that there's two solutions, positive 5i and negative 5i. We could have taken negative 5i here, negative 5i here, and we could have solved that, and I think you can convince yourself that that would indeed equal negative 25 as well. The reason is, if I have negative 5i here and negative 5i here, the negative on the outside there, well, those two negatives are multiplied to give me a positive, and then everything else in the problem is exactly what I have here. So it's going to give you the same answer. Plus or minus 5i is the solution to this problem. Okay? That's a lot to swallow. Really, that's going to be the gist of what we're going to work on in this section. And I think I want to take just a second here before we move on and before we work on some more actual problems to tell you that imaginary numbers, and we'll learn in a minute when we talk about complex numbers, but imaginary numbers really are some of the most absolutely useful numbers in all of math, okay? You haven't used them much in algebra because they're not very useful in regular old algebra. But in calculus, they are absolutely indispensable. You will definitely be working with imaginary numbers all the time, okay? So get comfortable with them, work some problems, and don't convince yourself that there's just this weird, wacky thing oh, it's imaginary, it doesn't exist. Okay, it's very real, and you will find problems in math that you can't solve without imaginary numbers. Okay, so let's continue on. I want to go ahead and just continue giving you an overview. I've introduced what an imaginary number is. Now I'm going to give you the big picture. There are three kinds of numbers in general in this world. Okay, the number 4 is an example, and only an example of what we call a real number. Okay, it's real because it's exactly what you think it is: 4 pencils, 4 erasers, whatever. It's a number. Okay, it's a real number. Now, another class of number that up until today you haven't worked with is called imaginary numbers. 5i is an example of an imaginary number. Okay? You only really get into using these things when you have square roots of negative numbers. And we've seen how we can take this and when it's a solution of something and prove that it is indeed the solution. And what this means is this is the number 5 times the, quote, number I, which was defined by the square root of -1. The third class would be an example, would be 4 plus 5i. That is called a complex number. I think you can get to see why I hate the names of these numbers. Okay, they look off-putting. Real number, that's fine, that's cool. Okay, you know, this is everyday experience. Then you have these things called imaginary numbers, and it sort of doesn't make sense why they're called imaginary, and I've tried to explain why they're useful. And then what you have is the third class is if you take a real number, which would be this one, I'm going to denote that by RE for real, and you add it to an imaginary number, which I'm going to denote by IN, and you'll see this in the math, okay, in books. If you add them together, you can't really add them any more than what I've drawn here. It's like x plus y. You can't add them anymore either. You just have to kind of write it down that way and say it's x plus y. When you have a real number plus an imaginary number, that is called a complex number. This is the most general form of a number ever. It could be 3.765 plus 7.2i. That's a complex number. You've got a real part, you've got an imaginary part. It could be 3/4 plus 7/16 I. That's a complex number. You have a real part and you also have an imaginary part. Okay? That's the general form. Up until now in math, all through elementary school, intermediate school, high school, algebra, and so on, all you've dealt with is the real numbers. Okay? The real numbers. Remember that number line that we talked about in my very first course that I produced on the Math Video Tutor and the fractions through the algebra? We had this thing called the number line. Okay? And we said, here's the point 0. And we said, here's all the positive numbers. Here's all the negative numbers. And this goes to negative infinity, and this goes to positive infinity. Okay? And we said, those are all the numbers. Well, I lied to you. Those aren't all the numbers. That's only half the story. All the numbers that you've ever dealt with, all the fractions, all the decimals, everything, negative, positive, I mean, you could have a negative here. That would be a complex number as well. All those numbers, that's everything that we've dealt with up until this point. But I'm trying to lift the veil for you and show you that, in general, this is not the whole number line. There's also, this is going to blow your mind, another number line that goes up and down. This would be called the real axis. Okay? And this would be called the imaginary axis. Okay? Together, all the numbers you've worked on so far have been along this line. The imaginary numbers, the 1i's, the 2i's, the 3i's, they lie along this axis. So you might have 1, 2, 3, -1, -2, -3. Those are the real numbers. You also have numbers along this, like I, 2i, 3i, and so on, up, and -i, -2i, and so on, going down. Okay? So you have real numbers along this axis, and you have imaginary numbers along this axis. So if you were to plot the point 2i, it would just be here. If you were to plot the point 3, it would be here. If you were to plot the point 3 plus 2i, Okay? It wouldn't be on this axis or on this axis. It would be 3, comma, 2i. So this is sort of the same thing as saying 3, comma, 2i. This is sort of like a x coordinate, and this is sort of like a y coordinate. You end up here. Okay? But, and I kind of drew that there, so for that's 2i, yeah. I'm just trying to point out that your knowledge of real numbers was kind of limited up until now, and the whole thing really includes the imaginary numbers, and you will find that in calculus, and as we go through trig, we'll see some examples of this too, but as we go through calculus, definitely, you will see complex numbers popping up out of the woodwork at every opportunity. So as I already mentioned, the general form of a complex number, the general form is a plus bi. This is a number plus some number times that thing that mathematicians made up called I. Okay? So let's do a couple problems and see where we can go. Let's say we had a complex number, 3 plus 2i, and we were going to add it to another complex number, negative 5 plus 4i. And I was going to add those two complex numbers together. How can I do that? Well, remember if you have, I'm giving you a sub-example here to illustrate what I'm talking about. If you have 2x plus y, and you're going to add that to 3x plus y, how could you do that? Well, you should know how to do that. You add the like terms. 2x plus 3x is 5x. Y plus y is 2y. You know from your algebra that you can't do anything more with this because you've got some multiple of x, some multiple of y, and you just can't add those anymore. They're different things, okay? What I'm trying to point out to you is the complex numbers is no different than the knowledge you already have. This is a like term with this. This 2i is a like term with the 4i. So in that context, you can kind of treat the I almost like a variable, almost. So when you're adding complex numbers, 3 plus negative 5 is going to be negative 2 plus, this is a like term with this, 2i plus 4i is 6i. And that's the answer to that problem. And you normally write the real part first and the imaginary part second, just like we have it here. Okay? So when you're adding, you add the real part, you get a number. You add the imaginary part, you get a number. Okay? Let's do another one. Let's say we have 7 minus 3 minus 7i. So this is just a number 7. And this is a complex number, 3 minus 7i. One thing I want to point out to you, this number 7, this is sort of an aside here. This number 7 is really 7 plus 0i. In fact, every number you've ever known up until now has always been that number plus 0i. If you're talking about a fraction, it's 3/4 plus 0i. If it doesn't have an imaginary part, which is all the numbers up until now we've known, they have 0i tacked onto the end. So this is just 7 plus 0i. So in order to add these complex numbers, I've got to add like terms. This is a real number. This is a real number. I can add them together. But before we do that, I want to simplify this a little bit. I want to distribute this negative 1 here that I have sitting out kind of in like this. So I'm going to have 7 minus 3, negative 1 times 3 is negative 3, plus 7i. Negative 1 times negative 7i gives me positive 7i. And then finally, I just add the real numbers together. 7 minus 3 gives me 4. And then I still have my plus 7i left over. And I can't do anything more with this because now I have a real part, I have an imaginary part, and I can't add them anymore. So this would be the answer. Okay? So you can see this stuff isn't really hard. You have a complex number and you just add the real parts, you add the imaginary parts. No sweat. Now let's try some multiplication of complex numbers. What if you had 4 plus 3i times negative 1 plus 2i. Okay? Plus negative 1, or times negative 1 plus 2i. I'm going to get rid of this up here for right now. Okay? Before we go and dive into this, there's one thing you should always have in the back of your head when you're dealing with complex numbers. The first is what I've already told you, that I is equal to the square root of negative 1. You should just memorize that. The second follows directly from this. I squared, I times I, is just equal to negative 1. And that makes sense. If you square both sides, you're just going to get negative 1 back. So I squared is equal to negative 1. You must remember these two things. My goal is to teach you what you need to remember and not to bore you with a bunch of things you don't. You have to remember this, okay? So let's continue here. This is just sort of like a polynomial times polynomial. So I can multiply these with the FOIL method just like I can if it was like x plus 3 times x minus 3. So first thing I'm going to do is multiply the first terms. 4 times negative 1 is negative 4. Okay. The outside terms here, 4 times 2i is going to be 8i. It's just 4 times 2 is 8, pardon me, times 1 gives you the 8i, just as if it were a variable. Then you've got times the inside here. 3i times negative 1 is negative 3i on the inside. And then finally you've got the outside terms. And I'm going to slow this down a little bit for you so you see it. 3i times 2i, 3 times 2 is 6, but I times I is I squared. Now, if this were a real variable, like x or y or something, then I would just kind of slow down and stop here. But this is I squared. We know what I squared is. It's equal to negative 1, so I'm going to use that. Moving along, I've got my negative 4. 8i minus 3i is, remember they're like terms, so that's 5i. Okay? And then finally, I've got, for my last term, 6 times I squared. We've already defined I squared as negative 1. You're just going to have to remember that. Okay? So, I've got negative 4 plus 5i minus 6. So finally, I think you'll see negative 4 minus 6 is negative 10 plus 5i. Negative 10 plus 5i. That's the real part. That's the imaginary part. So you see, it makes absolute sense. You've got a complex number here that consists of a real number plus an imaginary number. Okay? You've got another complex number here. It's a real number plus an imaginary number. That gives a complex number. So you've got a complex number here and a complex number here. You multiply these two complex numbers. Whatever path you go through in the woods, you should end up with another complex number, which consists of a real part and an imaginary part. I've already told you that every number in the universe is real plus imaginary. And so when you do whatever it is you do to this stuff, you should always get some sort of complex number, and that's what we have here. The only thing to keep in mind is you can combine like terms, just as if the I was a variable, and also that I squared is equal to negative 1, and that'll really keep you out of trouble. And that'll really go a long way. Now I'm going to keep this up here so we can reference it as we continue on down. Let's pick up the pace a little bit and say we have negative 9i times 4 minus 8i. Well, I'm going to distribute this 9i in just like I would if this were some other equation. Negative 9 times 4 is negative 36, but don't forget your I, so that tags along. Negative 9i times 8i is positive 72, 8 times 9 is 72, I squared. Okay? Which equals negative 36i. Okay? I squared is just negative 1, so I'm going to write this as minus 72. I squared is negative 1, so if this is 72 times a negative 1, I can move that out in front and make it minus 72. And of course, to write this in the proper form, my real part needs to come first, negative 72 minus 36i. Okay? Not too bad. Try something a little bit different. What if I have 1 over 3 plus 2i? At first glance, it would look like this is absolutely simplified already. But remember back from just from algebra, that if you have 1 over like the square root of 3, mathematicians don't like to have square roots in the denominator. Well, they don't like to have imaginary numbers in the denominator either. And so basically when you see a problem like this and the thing says simplify this for me, what you need to do is figure out a way to get this out of the denominator. I'm going to show you how to do that. What you do is very simple. 3 plus 2i. I'm just writing what I have. All you do is you multiply top and bottom by what we call the complex conjugate. Now is a good time to talk about the complex conjugate. I'll just write it here. All it means, it's a very, very simple concept. All it means is anytime you have a complex number, like let's say your complex number was 3 plus 2i, the complex conjugate would be 3 minus 2i. All you do is everywhere there's an I in your number, you put a negative in front of that term. Okay, so if your imaginary number was 2i, well, let's change it a little bit just to make it just that much different. 10i, okay, with no real part, okay, the complex conjugate of that would be negative 10i. So you just put a negative sign in front of any imaginary term. Here's a bonus problem. What if I give you the number 3? It has no imaginary part. What's the complex conjugate? Well, the complex conjugate of 3, if it's a real number, is just 3. There is no imaginary component, so you can put a negative in front of it, but it's just going to yield the same thing. So what you do, now that we know what a complex conjugate is, what you do is you multiply top and bottom by the complex conjugate of the denominator. 3 minus 2i over 3 minus 2i. Now you know you can do this because what you've essentially multiplied here is by 1. This over this is just equal to 1, and so yeah, I can multiply by that, that's no problem. And you will see why multiplying by the conjugate is very useful. On the top you will have 3 minus 2i as expected. On the bottom you will have this times this. So to speed things up, I'm going to put parentheses around this term, parentheses around this term, and I'm going to do FOIL on multiplying these right there. 3 times 3 for the first term is 9. 2i times 3 gives you 6i. 2i times 3 gives you 6, and don't forget the i. The outside term, 3 times negative 2i is negative 6i. 3 times negative 2i is negative 6i. And for the final term, I'm going to be very cautious about this final term because it's easy to screw yourself up. 2i times negative 2i is going to be negative, because negative times positive gives you a negative number. 2i squared. Okay? Negative sign there, and then you've got 2i times 2i. And in fact, you know, that's fine, but really I want to just write it this way. Negative 2i times 2i. The negative comes from here, and then you've got 2i times 2i. I think it's clearer if I do it that way. First thing you should notice is this 6i cancels with this negative 6i. They disappear. So what you're left with over here is 3 minus 2i over 9. Then you've got a minus. 2 times 2 is 4. I times I is I squared. Okay? Equals 3 minus 2i over 9 minus 4. I squared is negative 1. Okay? So what you're going to have here is 3 minus 2i over 9 plus 4, because negative times negative gives you a positive 4. And then finally, you're going to have 3 minus 2i over 9 plus 4 is 13. Okay? 3 minus 2i over 13. And then you can even split this up more if you want to. It's not required, but you could just say, okay, well, that's 3 over 13 minus 2i over 13. And you can convince yourself that's true because the denominator is the same, so if you just add the numerators together, you get back what you started with. Okay, let's review what we did here. We started out with this. We wanted to simplify it, so we multiply by what we call the complex conjugate, which is this, on the top and the bottom. On the top, it's very simple. That's what you have. On the bottom, you have to do FOIL. The reason you pick the conjugate was so that you get some cancellation from the inside and the outside terms there. That will always happen. Anytime you multiply by the complex conjugate, you will always have these terms drop away, which is why they're useful. Notice when I got to the last terms, I was very careful to write it out exactly right, not skip steps, because it's tempting whenever you work these for a while that you know I times I is going to give you a -1, but if you're not careful, you can screw yourself up on the signs. So I wrote it out very carefully. The bottom became 9 minus 4i squared, which I took the I squared, made it a -1, and I just kind of went through this, and you end up with a relation that has a real part and an imaginary part. And that's where you ended up. So that's how you simplify something like that. I'm going to do a couple more problems, and we'll call it quits for this section. What if I wanted to simplify 4 minus 3i over 2 plus 4i? And the question was, simplify that. Okay. Well, I would do the same thing I did before. I don't like to have complex numbers in the denominator, imaginary numbers in the denominator. So what I'm going to do is I'm going to multiply by the conjugate, 2 minus 4i over 2 minus 4i. So to get the conjugate, you just put a negative sign anywhere there's an imaginary number. That's your conjugate. On the top, see, I got parentheses basically around all this stuff. It's going to help me group my terms. I'm going to do FOIL on the top. For the first term, 4 times 2 is 8. For the outside term, 4 times -4i is -16i. -4 times 4 is -16, and you got the I that carries along. -3i times 2 is -6i. Okay? And then for the last term, -3i times -4i. Well, you got a negative times negative, so that's going to definitely give you a positive off the bat. 3 times 4 is 12, and I times I is I squared. Okay? So, again, negative times negative gives me positive. 3 times 4 is 12. I times I is I squared. We'll deal with the I squared later. On the bottom, first term, 2 times 2 is 4. The outside terms is 2 times -4 gives you -8i. 2 times -4i, -8i. Inside, plus 8i, because 4i times 2 gives you this. And then the last term is negative times positive gives me negative. 4 times 4 gives me 16. I times I gives me I squared. Now notice right away, on the denominator, you get an 8i that cancels with an 8i there, which is exactly the reason why we did this. On the top, we have 8, okay, minus 16i minus 6 is 22i, -22i, plus 12i squared, okay? I squared is just -1. So this is really a -1 sitting out here, this term. So really it's minus 12, because this is like 12 times -1. On the bottom, you've got 4. Of course, your 8's canceled. Okay? And then you've got -16. I squared is -1. Okay? So that's, I'm going to group my real numbers here. 8 minus 12 is -4 minus 22i. I just added these terms together, and I got -22i. Okay? And then on the bottom, what I really have is 4 plus 16, because negative times negative gives me a positive here. And so in the end, I've got -4 minus 22i over 4 plus 16 is 20. Okay? And I can continue simplifying that. If I want to put it in terms of a complex number, I can say this is going to be -4 over 20 minus 22i over 20. I just split this fraction up into two fractions because I've got a common denominator. You can convince yourself that if you were to add these fractions together, you would get that. Okay? And then I can simplify this fraction. I can see that the number 2 will go evenly into the top and the bottom. 2 times 2 is 4. 2 times 10 is 20. So that's that one. Okay. Over here, 2 times 11 will give me, or 2 times 11i will give me 22i. And 2 times 10 will give me that. And then finally, I can see that this will simplify further to negative 1/5 minus 11i over 10. And that would be the answer to that problem, fully simplified. Here you would have a real part, and here you would have an imaginary part. So all these problems, when you go through all the mess, you're going to get a real part and an imaginary part. It's very important to be comfortable with imaginary numbers. I can't stress that enough. Some topics in math are pretty boring, but complex numbers, man, that's really useful stuff. Okay, we'll do this final problem. What if you had an equation that said x squared minus 3x plus 10 equals 0? And this is just regular old algebra, and I said solve that equation. Well, the first thing you would do is try to factor it. You would try to factor it and come up with something like this and try to solve that. Okay, that's not going to work though. We're just going to save time and tell you that right now. So you can also use the quadratic formula, which is, to remind you, negative b plus or minus square root b squared minus 4ac all over 2a. And if this looks foreign, then go pick up my Algebra 2 DVD and you'll go through all this stuff and why this is true. But basically it's simple. The coefficient in front of x squared is what we call a. This number here is b, and this number here is c, and really you just plug it in here. I mean, there's no big deal. So in this case, a equals 1, b equals negative 3, c is equal to 10. A, b, c. So let's plug it in here and see what we get. X is equal to negative b, but b is negative 3, so that's just positive 3, plus or minus square root b squared. Negative 3 times negative 3 is positive 9. Negative 3 times negative 3 is positive 9. Minus 4 times a, which is 1, times c, which is 10, all over 2 times a, which is 1, like this, equals 3 plus or minus square root of 9 minus 4 times 1 times 10 is just 40 over 2 times 1 is 2. Okay. This equals 3 plus or minus square root of negative 31. 9 minus 40 is just negative 31 divided by 2. Now, if you hadn't gotten to this far in your studies of math, and you had gotten an equation like this in Algebra 1, you would have no idea how to solve this problem because you have a square root of a negative number. And you wouldn't know how to do it, okay? But now that you know that the square root of negative 31, you know how to do that, you can proceed, okay? So how would you proceed? Well, what you would have here is, I'm going to split this up into two things here, and you'll see why. 3/2, 3 over 2, plus or minus 1/2, which is this 1 from here, this coefficient in front of here, over 2. And then the magic part is the square root of negative 31 is just going to be 31 square root of 31i. Okay, and that would essentially be the answer to the problem. Okay. You really can't take the square root of 31. There is no way to really operate on this and actually get. If you put the square root of 31 in your calculator, you're going to get a decimal. Okay. There's no way to really to get it like square root of 25 is just 5. Well, that doesn't work for 31. You can't do that. So what you do is you go ahead and you take the square root of it, all right, of this number here without the negative sign, but you can't do it. So you just leave it as the square root of 31. positive 31, and you slap an I at the end to remind yourself that, hey, there was a negative in here, so this is an imaginary number. Okay, so the answer to the problem is this. You get a real part plus this imaginary part, that would be one solution, and you get a real part minus this solution, and that would be the imaginary part for those two complex numbers, and they're both solutions of this equation.